So today I'll be discussing on sympy. I would like to say that so far, whatever we have discussed is something which we can call the essentials of Python. If one wants to write codes in Python, develop, these things are absolutely necessary. But today I'll be talking about sympy, which I would like to describe as something like a happy side trip. I mean, one can avoid this. I mean, this is not essential, but it is an interesting module. Many of the participants may enjoy this, and particularly those who are not very, those who do not enjoy numerical calculations much. They consider computer to be untouchable because whatever computer does, it doesn't understand that x plus y whole square is equal to x square plus 2xy plus y square. So it's garbage. So I'd like to see whether we can do such things in computer also. But those who are familiar with Mathematica, Maple, and MATLAB, they already know that these things can be done. But let me tell you that none of them is free. But Python gives you as in free, so you can have your symbolic calculation module in your sympy. First of all, let me tell you that this is not a part of the basic Python. So what you have to do is a third-party package kind of thing. So you have to, if you don't have Anaconda, you have to install it using pip install sympy. But the beauty is that that's why I've become a fan of Anaconda, that it comes along with Anaconda. So we will try with sympy. And my spider is open. So let me first see how do I use sympy. Like any other module, let me first input everything from sympy. Doesn't matter. From sympy, import star. Okay, everything is imported. Now I have to create, I'll try with the symbols, not variables. So I have to create a symbol. X is a symbol. So X.
Arunabha, I just interrupt you. Here we can use a star, import star, unlike a NumPy star.
No, I just wanted to pour down everything here. So from sympy import star, that is why I did. And Kishore, I didn't get you. What is the exact problem?
Actually, from NumPy import star, it is normally
We didn't do
avoid.
that because that gives you too many things. But I just wanted to keep it simpler. That is why. I mean, it is definitely not very advisable way, but let me do that. I mean, for the time being. So,
Okay.
so x equal to sympy a symbol symbols x. That means x is a symbol. Let me introduce another symbol also. Xy. Xy two symbols. So xy's are not variables. They cannot store values. They are symbols. Now let me just say expand x plus expand is a function. What should it expand? It should expand x plus y whole square. Let us see whether it understands the meaning of this statement. Apparently it gives some output, but I'm sure you cannot see what the output is. There's a red out 3, and just below that there is some very vague thing which even I can't read. So let us do a trick. It is trying to be very smart. Let us make it a bit unsmart. Init printing is a function which tells you how to print output. You can see that the very fast argument is pretty print equal to true. It's trying to print things very in a pretty way, and that is why it's becoming too smart. Let us make it a bit unsmart. So pretty print equal to false. Don't have to be that smart. Now issue the same statement again. Now you can see it says x square plus 2xy plus x square. So it knows the algebra, this symbolic algebra. Put it 3, we can have this. So we can continue our discussion in this forum, in this using Spider. But since I have made I made my Spider a bit unsmart, I'm not getting the full fun of sympy. So to enjoy the full fun of sympy, let me open the whole thing in a different ID altogether. And this is called Notebook, which comes along with Anaconda. To start Notebook, I'll go to command and type Jupyter Anaconda Kim. I just click that. It will take a few minutes. And see, my Chrome is open. My Chrome is open. My Chrome, which has this Meet window and some WhatsApp window, and a new window is open, which is the Jupyter uses the Chrome windows. Okay, now I'll start a new file. Here, new Python 3. It's a programming environment. See, it is waiting here. It is something like a interactive cell. Here I can put, say, 2 plus 3. But if I enter, nothing will happen. Although it looks like a interactive environment, it is really. But in order to execute this program, I have to press this button, run. See, 2%3 is everything. So I can go back to the previous. This is called cell. I can go to the previous cell and change this. I mean, so let me work out here. So what I was doing from sympy import star. Enter, because I'll be doing something, right? Because it's a cell, it can handle multiple lines. So all I can type multiple lines and execute like a script. So the next thing is what was there? So x, y, z, t equal to symbols x, y, z, t. So these 4 characters will be reserved as symbols. Okay. Then I say expand. I think
can you try increasing the font a bit?
Right. That's what I just realized, that my font size is too bad. Is it okay? This is, I think, okay, right? Okay. So expand.
An attempt to increase the font size over the left. They lost connection. Just give us a minute until we figure out what went wrong on this end. তুমি কেটে গেছে তোমার কি কেটে গেছে? হ্যাঁ দেখো তুমি আছো কি? So apparently Arunabha did not realize that.
Perhaps the connection is lost, I think.
Yeah, he lost his connection. He didn't realize that, so he has kept on talking. So I
Okay,
had to
okay.
call him up. So he's trying to reconnect again. Yeah, he's back. No, Unabodha is back, right?
Can you see? Yes, can you hear me?
Yeah, now I can hear you.
And can you see
Right, you're
my
back.
presentation also? Okay. And you can
I
see my
can see your
presentation also,
presentation. I can
right?
also see you. Yeah.
Okay. Now, I think now I was discussing up to this. I just said that I did everything that in the, I mean, I repeated everything that I did in Spider, but only that I used the NumPy notebook. And in the notebook, the advantage of using notebook here, at least in this step, that when I did expand x plus y whole square, I got a very nice output. Definitely, it looks much better than what I saw in Spider. So, if you have to use SymPy, I would always advise that you use notebook cells. And as I said, another thing that SymPy contains a lot of functions and modules. I cannot exhaust them, and it is not necessary either. I just show you some functions, and I would, if you are interested, then go to the tutorial of SymPy, which is available in the net. Google, find it out, and those are very much self-explanatory. Try it yourself. You will find the kind of thing that you want to do. I'll just show you some examples. Like I said, let's see, series of log of 1 plus x as a function of log of 1 plus x. This is not necessary. Log of 1 plus x as a function of x. See, what I can do, I can mention the point about which the function has to be expanded. Like I can say log of x expand around 1 and keep, say, 8 terms. Right? Okay. So, so that is it. Series. So I can similarly have more complicated expressions like log of sine of log of, say, I can make the things complicated and uh, get things done. And next interesting thing would be limit of, say, sine of x by x and in the limit I have to specify x tends to 0. Let's see, gives me 1. Let me calculate another limit, something that I know answer to, say 1 plus x by, only have variable x, symbols x, y, z, t. So I have to use one of them. X by y to the power y, y tending to infinity. So how do I write infinity? 2 small o. This is e to the power x. Usually we write it with n, x by n whole to the power n, but I didn't define n to be a variable, so I have to use one of the variables that I've already defined. Okay. I can also do integration, like integrate the sine of x with respect to x. Minus cos x. Okay, it's quite good. The sine x minus cos x, this is indefinite integral. But if I want to do a definite integral, integrate sine x from, put a bracket, perhaps bracket, I don't remember, 0 and pi 2. A comma here. Let's see. Yeah. So this is the way to do. If I simply say x, it will do an indefinite integral, and if I put on like this, x 0 and pi by 2, it will do an definite integral. And then say I want to solve an equation like I want to get the roots of the function x to the power 4 minus 1. Let me see what I'm solve. X to the power 4 minus 1 is the function whose root I'm searching for. So see, it gives me minus 1, 1, minus I, and I stands here with a capital. So minus 1, 1, minus I. So there are 4 roots. And I can have solve set. Oh, sorry, this is solve. Solve set would be, is actually finding equation x to the power 4 minus 1. That gives you a better output, I think. Yeah, solve set. And solve is for systematic equation, system of equations. Like if I want to solve a system of equations, like say solve, say x plus 2y equal to 1. I'll write the left hand side only. So this stands for an equation x plus 2y equal to minus 1. And another equation, say 2x minus 3y equal to, say, 9. So minus 9. Let's see. Solve for x and y. There is a oh, sorry. Definitely there is a syntax. Let me see, what did I do mistake? Okay, just a minute. Oh, I have to put them in a bracket. Yeah. So come here. Yeah. Clear? I've solved 2 equations, x plus 2y minus 1 equal to 0 and 2x minus 3y minus 9 equal to 0. Simultaneous solution of these 2 equations for x and y gives me this. And then let me try a very simple plotting. Like plot of sine of x. Plot of sine of x. See, if you can't see, I have to reduce the. You get a very nice curve, and I did not specify the limits within which I have to draw. I can always do that by saying, say, x equal to minus 2 star pi to plus 2 star pi. So say minus 20 to plus 20, let's say. Because here it is from minus 10 to plus 10. I have to see that I could change this. Yeah, say from minus 10 to plus 10. So all I have to do is to, within the bracket, I have to mention the limits. That's it. Let's try to plot two functions together. Like plot x to the power 4 x cube minus 2 x, 2 star x, and also x4 minus 3 star x. Say, just let me plot this from, say, x equal to say minus 3 to plus 3, anything. Let's see what happens. I can see two curves, but definitely if I'm very dumb, I can make out which one is what, right? So let's try if I can do give some sort of difference between these two simultaneous plots. So I would first try legend equal to true. Does that help? Legend equal to true. That gives me a legend, but doesn't help me much because both are drawn in the same color. The best thing would be to use two different colors, but here it is not very simple. I mean, what I have to do is to write show equal to false. That means you don't show the plot, okay? And so there are two plots I don't want to show. And then I say P1, sorry. P1, at the second plot I mean, comma line color equal to red. And then P equal to P dot show. First of all, you have to store it somewhere. So I don't want to show it, but I want to show the whole plot object as P, and then the plot object has two plots. The second plot, P1, I line color made red. And then I said now plot dot show. Let me see what happens. Sorry, it's not P. P is the name of the object whose one component I'm going to change. Now I'm done. So x to the power 4 was my second plot, which is now in red, and the blue one is here. So I can see the difference between. Of course, I could see because there are many other ways to find out, but let me say that I'm dumb. I cannot make out. So this is the way to do it. I've been able to color them in different colors. So this is about plot. And then I'll show you something more. like matrix, matrix of symbolic matrix, I have to store the matrix somewhere. So let me write any alphabet, uh, equal to matrix of yeah, list of list. Say X.
Arunabha, could you just increase your font again?
Yeah,
I think
yeah.
the one better gardening font.
So this is the first of all, let me this one. What is this? Does it accept this? No, I have to put a comma here. The matrix. If I say matrix, and it's something like numpy, it's a list of list. Instead of saying np.array, I said matrix. xy, yx. So a nice matrix is created. Let me store this matrix somewhere in some variable. It's not variable. It's because it's a function made out of symbols, so it is also a symbol. So now I calculate m dot trace and m dot depth. These things we can always verify. Okay, let me put this one here so that everybody can see. Print m and this. No, right this way. That is better. Just m and run this. I get the matrix and run this. So the matrix, trace, determinant, everything. The algebraically I can find out. Okay, and let's see if I can do something more like m dot eigenvals, m dot eigenvals. It tells me that there are two eigenvalues. One is x minus 1. Colon 1 means that x minus 1 occurred once. It's and y x plus y colon 1. Colon 1 means x plus y also occurred just once. So x minus y occurred once and x plus y occurred once. So I got two eigenvalues. If I want to get the eigenvectors, then I have to write eigenvectors or vect, I forgot. Let me see. Yeah. Again, I think I have to reduce a bit. See, it says that x minus y is the eigenvalue which occurred 1. Corresponding to that, this is the eigenvector, minus 1 plus 1. And x plus y is the another eigenvalue, which occurred once, for which this is the eigenvector. So it's quite pleasing. Now I want to show you differential equation. Integration I have shown you, and I have to show you differential equation. Say I have to let me solve a differential equation. I'll show you what kind of differential equation I'm going to solve. First, let me define a differential equation and let me solve this. So first, x equal to, x was a symbol. Now I want to make x something else. It is not a symbol. It's a function. X is defined as a function, an unknown function, which I'll find out. X is a function of function. So it means x is not a symbol, it's a function. Function of what? Function of t. T, you see, I've already defined as a symbol. So T is defined. So X is now not a simple symbol. It is a function of T, right? And next I defined some variables, a dx dt, some symbol rather say, which is equal to x if t. Here x differentiated with t. X is a function, so I can differentiate with respect to t, and whatever comes as a differentiation of must be another function, so I call it dx dt. And then I define an equation. First, let me call it EQ1. It's a function, EQ1 equal to dx, dx dt, that is the dx dt, comma, minus x. So what kind of thing it actually refers to? Let me first store it in a variable and just let me see what it is. Sorry. It is not EQ1. It is EQ. EQ is a name of forming an equation. It's a command, and I'm storing it as small eq or anything E1. EQ is a like function. This is a sympy function. This is also a sympy function which generates a function, and this is also a sympy function which forms an equation. Okay, so let's run this. See, this is the differential equation that I have formed. The syntax is clear that I have to write EQ, then the left hand side of the equation, comma, the right hand side of the equation. EQ, within bracket, first the left hand side of the equation, comma, the right hand side of the equation, right? So it's clear. So what it is this. Now I have to solve this equation. It's very clear. Solve E1. E1 is my equation. Just solve this. Differential equation, solve this. See the solution? We are quite satisfied. Solution must be C1 e to the power minus t. So we got that correct. So that we can make the equation a bit more complicated if we like d2 x dt2. 2x dt2 is dx dt if dx dt was the first derivative, so I differentiated it further, so it gives me dx dt d2x dt2. So let me change my equation. d2x dt2 equal to minus x. So what this equation is now, d2x dt2, let me see. I'm satisfied. This is my equation. So let's solve this equation. I'm quite satisfied. C1 sine t plus C2 cos t. But then we would like to fit some sort of boundary condition and get the value of initial condition and get the value of C1 and C2 also. So let's put it here itself. ICS, initial conditions at x equal to, at x at t equal to 0, x at 0, x at 0 is 0 and dx dt at 0, say equal to 1. Equal to 1. Let me see if ICS is this. ICS, probably ICS needs a, let me see if it says wrong, I'll change it. Yeah. Let me see. I made some mistake. Oh, within a second bracket. ICS comes with a second bracket. Okay. It's difficult to remember the syntax. ICS comes with a second bracket. Instead of first bracket, I have to give a second bracket. Is it okay? No. X. No. Let me see what it was. Oh, X dot substitute. Sorry. X dot substitute T0. Substitute T0 is 0, and here also dx dt dot substitute T0 what you want. Let's see if it is satisfied. Right. So let me clarify this. So E1 is the differential equation that we solved, and we got C1, C2. We wanted to evaluate the CN C2 by using the initial condition. So this is ICS is the initial condition where X, I want to say that at T equal to 0, X is equal to 0. So I would say that substitute T equal to 0 in X. T equal to 0, what if you put T equal to 0, then take X equal to 0, and in dx dt, put T equal to 0, dx dt should be equal to 1. So that is the syntax, and I will get a thing like that. This. Now, this is also quite nice, and I want to show you another thing here. Why this one? Let me open something from the running code. Downloads. Yeah.
Monkey.
Sorry. Okay, it is slow. Why? I don't know why. Yeah. Sim demo. Yeah. Yeah. This is a living code. Now, say I have here the same thing. I have this. This is almost I've described these things. So I have used WB2 symbols, which I'll not use it. Say I've taken a differential equation. So x is a function of t, and then d2x dt2 is this. I can straight away define them in one goal, and dx dt is this. And my equation, you can see that d2x dt2 plus x plus 0.1 dx dt. And in the right hand side, I put sine 1.1 t. So the equation becomes something like this. So it's actually a forced damping oscillation. This is the d2x dt2 plus damping term is 0.1, and natural frequency is 1, and the forcing frequency is 1.1, very close to the resonance. So first of all, let's just put S. Let's see. With the boundary condition that at t equal to 0, x is equal to 1 and dx dt equal to 0. X equal to 1, so it was, there's an initial amplitude, but the velocity was 0. So I just run this. Why? Did I do any mistake here? Q1, what does it say? I'm very sorry, because it's a new file. I didn't run this one. It's completely new file, so I had to run the first line, of course. So hash this, put this. EQ1 is not defined. Yeah, EQ1 is defined in the previous line, which I didn't do. EQ1 and it gives me a solution. This is the solution of this equation bound to this boundary condition, right? Okay. So probably things are going right. Did we see if I do simplify, does it help me a bit? Still working? Yeah, not very much. So it's giving me a kind of solution. So what I want to see a graph of this. What is the kind of graph of this? So it's a very complicated thing. I want to see a graph of this. So what I have to do here, because it's a very complicated function, I want to do a graph. The thing would be that you first go to a typical NumPy kind of thing. NumPy, because I ran this cell, NumPy is already imported. Okay. NumPy is already imported. So so I can run this program. Some key points are created from 0 to 40. 401 points are created. Now, this is the important thing, that I have to create something called a function from the solution. This is a solution. This is a solution, this is a relationship, the symbolic relationship that xt equal to this. It's a kind of equation, symbolic relationship. But although I want to call it a function, it's not really a function. It says xt equal to this. It's a symbolic relationship. But the right-hand side of this is a function which I want to plot. So I have to make the right-hand side a callable function. So that is it. That is called, from the, in SumPy there is something called utilities module. Within the utilities there is a function called lambdify. So I have to use this function utilities.lambdify, which makes a function of t. Function of t what? From the right hand side of s.rhs. S is this. S is the entire this thing, which is a relationship, between xt and this. This is the left hand side and the right hand side. The right hand side is I want to make a function out of this right hand side. So I use this facility utilities.lambdify, and that it takes the s.rhs, the right hand side of this equation, and makes me a function. And I use NumPy because it will be a vectorized function. If it is a vectorized function, then now it becomes something like a normal NumPy utility. So I'll just operate Sn on the entire t, I'll get an x, and then import matplotlib and run this and get the plot. So now I can change things like this. Say instead of this, I go to say a different frequency, forcing frequency further from the resonance, say 3, and then run this. It gives me And so this equation is now changed, 3t, run this function, solution is got, and I want to plot this. So this is where I would like to stop. I mean, there are many other utilities. Okay, this is also interesting that this is an error function I integrated and give me the result root pi as it is. Okay, here I would like to stop just to make a comment about this notebook facilities. If you look at my notebook, you can say that here this is a live function. I can always always run any of these sub functions, and these are outputs. And here, besides the live functions which I can run, change, run, and do everything, and get the functions, like instead of 4, I can write 3 and run it here. Besides them, I've also used this kind of things. It's just any window. For example, this window. This window was originally something like this. Instead of typing the program, I typed some simple language, and then here is I went to Markdown and then ran. When I went to Markdown and ran, the whole thing that I typed, there's a language called Markdown language, which helped me to create such a nice little display of the notes, and the details of the Markdown language can also be found using the tutorial, and usually they're very simple, very close to LaTeX. Somebody, if you know LaTeX, you can simply type LaTeX here, and there are a little bit of things taken from HTML and all, so you can put beautiful notes here and there, like the one I did. Square root of 60, if you type, it get 2 root 15. It's very strange because a numerical computation would yield a floating point number, but this is more pleasing to the theoreticians. And here also, for example, here I said that O stands for infinity. This kind of a note I can go on writing in the notebook itself. That is the the utility of notebook. Say here itself, I've used the integration it's a note itself. I can use mathematical expressions using my LaTeX. So I don't have to do anything. Just use the LaTeX language, and it understands the LaTeX language and does the compilation for you. So if you want to do such an integration, that you can use such a note. That is one of the beauty of using the notebook. Okay. I think I should stop here, and if there is any
some question is there. One question is from Shaheen Nasreen. Can you explain boundary conditions once again?
Yeah. You can see this boundary conditions. Yeah. See, sim demo. Yeah. See, this is my equation. And I solve this. This is my equation, second order differential equation. I solve this. So I have to give two initial conditions at t equal to 0. What is the value of x and what is the value of dx dt? The syntax is you start with ICS equal to, then within a curly bracket, you have to say, I want to say x at t equal to 0 is 1. The style is this: x subs t equal to t comma 0 is 1, colon 1. That means at x t equal to 0, x is 1. The way to write it is this, and at t equal to 0, dx dt is 0. The way to write it is this. You can change the condition and get different results. For example, make this 0, make this 1, run this. No, what happens? This was 1, this was 0, then it took happily. Oh, perhaps this was not run. Let me run this. previous cell was not run perhaps. Yeah, it gives me a solution. Now change the initial values. Yeah, give me the solution. See the function. I mean, see the graph. Here it is. So
Another question from Tania Bhattacharya. Can we have symbolic parameters in the differential equation?
yeah, of course you have. You can have. Of course you can have. But you cannot have the graphs. For example, let me just show you. Where it is. Where am I? Yeah, that is. I already had the omega as a symbol. So like here you put B, right? And here you put, say, omega square. Let's just make it a simpler one, right? 0. Like make it omega square. Omega square. I believe I'm omega square is this. So let's see the function first. No, I did some mistake somehow. Oh, this one to be run first, and then this one. So we are having some parameters, and try to solve this. See, we've got a solution.
Another question from Rudro Narayan Mondol. Can we draw Lissajous figure using sympy?
I have not personally tried, but you should be able to do that. I don't know.
And using numpy and matplotlib, it will be trivial.
Definitely.
Even dynamic ones, things
Right.
which move.
Our time has finished. If you have any other queries, please you can ask in WhatsApp group. Discussion can be continued there. And
just to tell you that this time I'm not going to share the slides. Rather, the beauty of the NumPy, I'll this notebook that you have seen. I'll just take a PDF copy of the notebook and send you so that you can open it using PDF reader, and also I'll share with you the NumPy number. I mean the notebook itself, both the PDF version and the notebook. So if you have installed Anaconda in your computers, you can run the notebook and do it yourself. So I'll share both. Right? Okay. Thank you.
so thanks to both the speakers for this wonderful session today, and it was really enjoyable. Thanks to the audience also for their patience to bear us. And
thank you, Bishwajit. Thank you, Dumo Hippo, Rudranarayan Mondal, everyone.
And we will come back again tomorrow at 3 p.m. So for then, goodbye.
Goodbye. Thank you. Nice.